Alright, gang, let's go ahead and get it going. Let's see. Alright, can I get someone in the chat to acknowledge my existence for that sound check? Thank you. I feel validated now. Ooh, Hunter's at level 7. And he's reminding us to record. Beat you to it, Martin. Alright, so we are recording. I think we're recording. Yep, we are indeed recording. Alright, any questions, comments, concerns? Let's see, Jacob saying, some of the last few lectures have not been uploaded to YouTube, and the last one that I uploaded has the wrong date. Okay, I'll take a look at that and make sure that's good to go. Bashir asks, can we go over the exam? No, we can't. If you want to come to office hours and talk about the exam, we can. But that is in the past. It is behind us. Speaking of that, the grades for the exam are up. The class average was pretty good, so no problems there. Well, everything in the class is curved, so... Not to mention the latest round of Python exercises are going to help your grades a lot, because they were pretty easy, and pretty much as long as you made a good, honest attempt, you're going to get 100 for them. So as long as you took them seriously, you'll get 100. So you're about to have a monstrous amount of hundreds dump into your Python project grade, unless you didn't do the projects, in which case you'll get zeros and you'll be sad. Bashir, no, the final is not cumulative. The final is just over this stuff that we've talked about since the last exam. So just this Python stuff. And we'll do a pretty comprehensive review for that exam. Yeah, man, we're trying to put that behind us. Back when I started the class like a old guy, worried about theory and nonsense like that, and realized there's a better way for us to live our lives by focusing just on application. All right. So if there are nothing else, or is nothing else, let's go ahead and dig into what will almost certainly be an extremely short lecture. The last half here of our Fourier transform. Turns out that we probably definitely could have done the last one in just one lecture, but I don't think anyone will complain about a 10-minute lecture. So let's dig right in. Why don't you go to the next screen? Okay. So just to do an overview, so last time we talked about the sort of lead up to this. We talked about the matrices. We talked about the synthesis problem. Now we're going to do the analysis. We're going to do the analysis with linear algebra, and then we're going to take a look at how to implement the DFT ourselves in the Python. So first up, the analysis problem. It's given here. It's the same thing as before. It's the inverse of the synthesis problem. It says, given a sequence of samples y, and knowing the frequencies that make up the signal, can we compute the complex amplitudes of the components A? And it turns out, well, we definitely can. And a lot of this is exactly the same as it was before, right? So we're still doing the outer product on this first line to create that list of products of time and frequency. And now, just like with the discrete cosine transform, we're passing those to 2 pi times the thing, but now remember we're doing the complex exponential, right? And getting values for m that are a complex number, and we're plugging them into this linear algebra function to solve for y, or excuse me, solve and get amps given m and y, and we're returning amps. So like I said, exactly the same as the discrete cosine transform, the only difference being that we're going to use the complex exponential instead of the sinusoid directly. And if we go ahead and test this out, We drop it in. We're just going to set a certain number of frequencies, or the number of frequencies that we have. We'll set that as in. We're going to run that analyze function to grab our new set of amplitudes. Right, ys is just a vector of length in, the frequencies, and then ts is a vector of length in. And then if we go ahead and describe, or just print out our value for amps 2, well, we get this series of complex numbers, right? 0.6, 0.2, 0.1, 0.5. And notice that there's basically, while there is a sort of, not really a complex component, right? It's 0 times all of these things. That the real components here are exactly the same ones that we used when we were looking at the discrete cosine transform, 0.6, 0.25, 0.1, and 0.05. So, any questions about the analysis function? Okay. I know we're breezing over a lot of these functions and stuff, but make sure you're paying attention. Make sure you sort of remind me to post these slides up on, almost at the GitHub, the Blackboard, because there's still going to be test questions that come out of this, even though we're kind of just breezing over a few of these things. So now let's talk about efficient analysis. So this is, analysis, but let's do it with our matrices. But here it gets a little bit different, right? We've already seen that solving a linear system of equations is slow. You don't want to go through a for loop. That's bad. For the discrete cosine transform, we used values. We picked our own values of fs and ts so that m is orthogonal. But now what we want to do for the discrete Fourier transform, we want to create an m that is unitary, right, rather than orthogonal, which means that the inverse of a unitary m is the conjugate transpose. So it's not just the transpose, it's the conjugate transpose, which means that we also sort of transpose and flip over the imaginary component. So let's take a look at what that looks like. If we say, all right, we want to pick up, 4 values for our frequencies. We're going to grab a range ts, which is equal to just a range of length in, and we're going to divide those values by n. And then we're going to grab some frequencies, also using the arange function of size n, but no dividing by n in this case. We're still going to calculate the outer product, and we're still going to calculate the complex exponential. So here, basically exactly the same, except we're using this arange function for ts and fs, and then dividing our ts by n. So we need to test and see if m is unitary by confirming that the conjugate dotted with itself is equal to the I function. We do that here with this function. So m star m is equal to conjugate transpose dotted with m. And if we do that, we should get that identity function, or excuse me, that identity matrix. And we will. So now let's go ahead and put it into the analyze function. Now the analyze function is going to be a little bit different from the DFT. Remember, in the discrete cosine transform, the analysis function was the DCT function, like they were one and the same. Here they're going to be slightly different. But if we look at the analysis function, we're going to start with the same stuff. We're going to pick values for ts and fs to get our arguments, to get that outer product. Use the cosine, the complex exponential to get our matrix m. And then all we're going to do here is do m dot, take its complex conjugate, transpose it, and then dot it with ys. And here we're going to divide by n in order to get the correct number of amplitudes. We got to normalize it with our sample size to get our amps. And so if we plug that all into a script here, we say n is equal to 4. We're going to say that our amps are 0.6, 0.25, 0.1, 0.5. We're going to grab our values for fs and ts like we saw before in order to get a unitary matrix in. Then we synthesize and get our y's using the function synthesize2 that we did on Monday. And then we drop that into our analyze2 function to get our new set of amps. And when we do that and plot our amps, check it out, we're going to get the values as we originally described them, right? 0.6, 0.25, 0.1, and 0.05. So now that we've done that, let's take a look at the DFT function itself. So we can't directly write an analyze2 function the same way we did for the DCT. It's not quite the same thing. This is because we've got to be a little bit more specific about what we do for FS and TS. So instead what we're going to do is, instead of synthesizing FS and TS to sort of give us the values we want, we're going to synthesize M directly with this function. So we're going to create our matrix M using this same technique. We're still going to kind of, in here, grab our TS and our FS in the same way, plot the outer product of TS and FS, feed that to the complex exponential in order to get our matrix M, and pass that back. And now we have an analysis, or an analyze3 function. Set the length in, synthesize the matrix, and then M dot complex conjugative n transposed the dot product divided by n gets us a value for amps. Now if we take this and actually write the discrete Fourier transform, it's going to look like this instead, which is exactly the same, right? We're still grabbing the length of our samples. We're still synthesizing a matrix that is the same length. And here we're doing complex conjugate, the transpose, and the dot product with y of s. The only difference is that we're not dividing by n in order to get our output function. And we return our amplitudes that way. So to test this out, let's compare it with the NumPy's fast Fourier transform function. So if we feed the y's of our function to our DFT method, or excuse me, our DFT function that we just created, what we're going to get, see, we got 2.4, 1, 0.4, 0.2. If we feed that same set of y's to NumPy's fast Fourier transform method, well, we get the exact same stuff, right? 2.4, 1, 0.4, and 0.2. So we can see that this is basically the exact same way that NumPy does our discrete Fourier transform. The inverse DFT is nearly exactly the same, except we will divide by n, and we're not going to take the conjugate of m. So if we write an inverse discrete Fourier transform function, same deal. We create a space n that's the same length as our signal. We're going to create a synthesis matrix that's n by n. But here we're just going to take the dot. We're not going to take the conjugate. We're just going to take m and dot it directly with y and divide by n and return those amplitudes. And I wasn't kidding, man. That was going to be a fast lecture. So just to recap, we hit the analysis problem. We looked at how to do it by synthesizing a matrix, and then we looked at how to implement the discrete Fourier transform. And it doesn't get much quicker than that. So, any questions, comments, concerns? I think you have an assignment due today, or is it due on Monday? I can't remember. Also, don't forget it's due tonight. Are there any questions about that assignment? Should be pretty straightforward. I think most of you guys are finished already. All right, and don't forget the capstone project looms. I've gotten a handful of emails about people struggling with the capstone project. My advice is don't overthink it. Just relax a little bit. If you do the stuff that we've already looked at here, you're going to solve that capstone project with no problems at all. So if you're finding yourself chasing some sort of crazy rabbit, that means that you're probably overthinking it. So, and doing it in a way that's much more difficult than it ought to be. So, if there's nothing else, then as promised, super short lecture. I'll see you guys on Friday, where we'll do whatever's next. All right, thanks, guys.